inverse will be, of course, the inverses in the opposite order, so we have to start with sigma p on the left, followed by sigma q, sigma r. And for the inverse, we have that the last two lines intersect. So we are back in the case 1, and we can write, so there must exist some line L and point M, so that the last two can be written as, so that the whole thing can be written as sigma M, sigma L, and we know this is a glide reflection. A glide reflection. So we know the inverse is the glide reflection. But we know that if inverse of something is a glide reflection, then the original, which is the inverse of a glide reflection, also must be a glide reflection. So glide reflection, hence, so is the original gamma. And we are done. So think through the details here carefully. But if we show that the inverse is a glide reflection, then we must have the original be a glide reflection as well. So in both cases, the product of three reflections in lines which are neither concurrent nor parallel must be a glide reflection. So we have a theorem. I'll erase this. The theorem will tell us that if we assume our premise, product of three which are neither concurrent nor parallel, of course they have to be distinct. For three distinct PQR, then gamma is a glide reflection. So, as a corollary, we have the classification of odd isometry. So, any odd isometry then is either what? Is either a reflection or product of three reflections. And if these three reflections are in parallel or concurrent lines, then we have a reflection again. But if they are neither parallel nor concurrent, then it must be a glide reflection. So any odd isometry must be single reflection or a glide reflection. And then we have classification of all isometries. Finally, the goal is achieved. Classification theorem any non-identity isometry is one of the following. Is one of the following four. It's either a reflection or translation or rotation or glide reflection. Again, gamma stands for glide. First letter G of glide reflection. Alright, very well. Only identity can be both this and that, otherwise each isometry which is not identity will fall into one of the four classes. Excellent. We have the theorem. So we achieved what we worked for half of the course. And just a small comment now to this theorem is that what can we do with about conjugating glide reflection? So let's say that we can use this theorem to figure out what are conjugates of glide reflections with various isometries. So in fact, let's take alpha arbitrary isometry. So let alpha be any isometry, and gamma is a glide reflection. Then we can say that alpha gamma alpha inverse must be a glide reflection. Why? Well, first of all, what about parity? What can we say about parity? Parity of alpha, of course, doesn't matter here. We have the parity of the conjugate equal to parity of the original, which is for glide reflection. If we start with glide reflection, having odd parity, then we end up with conjugate being odd as well. So is an odd involution or not? So we know that gamma squared for any glide reflection, can it be equal identity or not? Is never identity. Why not? Because it's always a non-trivial translation, non-identity translation. So we have that it's a non-involutive odd transformation. So if it's an odd transformation, we must be here or there. But here we only have involutions. So since it's an odd non-involutive isometry, we must fall under this part of the classification. So hence a glide reflection. Moreover, we can say precisely what its axis is. So if you think about it, what would be the line fixed by that? So we need some line which taken to alpha inverse of this line, then gamma would have to fix it, and then alpha will take it back. So it's easy to guess that in fact it will be the line given by alpha of L. Again, check. So and that concludes the podcast for classification of all isometries or glide reflections. See you next time.